I've started the live stream. Hello. We are not able to hear you. Hello, am I audible?
Yes.
Yeah. Yeah. Are you able to hear me?
Yes. Professor Sugisaki, I'm able to hear you. You're talking from your account or the TCG account? Hello, am I audible?
Yes, but yeah. Hello? Hey. So shall we start? Okay, so so those of you who are online, can you hear me?
Yes, sir.
I can hear you.
Tushti, can you hear me?
Yes, sir.
Oh, good. Okay, so
Bhanu, is this happening here in the physically in our center,
oh, okay.
or the whole thing is online?
Tushti, can you hear me?
Yes, sir.
Oh, okay. Fine. Okay, good. Okay, so let's start. Well, it's my pleasure to introduce Professor Kenji Sugisaki, who is from Keio University. He's in two different places in Keio, the Graduate School of Science and Technology, as well as the Quantum Computing Center. And as many of you know, he's also a visiting associate professor with us. And I think you've all had the pleasure of interacting with him for over a year now. Many of you probably know him better than I do through your interactions. But yes, I mean, I have known him for almost 5 years now. Professor Sugisaki is one of the best known quantum chemists who has been working on quantum computing for quite a few years now. And he had his basic education as an undergraduate in chemistry from Osaka City University, his master's and PhD in Osaka City University is now known as Osaka Metropolitan University. And then he continued in Osaka Metropolitan University after his PhD and held various postdoctoral positions, was an assistant professor, lecturer. And for about a year now, he has moved to Keio University. Keio University is one of the leading universities in the world for quantum computing. The first IBM quantum computing hub in Asia was set up in Keio University. And Professor Sugisaki is now associated with that. And he's the head of the chemistry group at the Quantum Computing Center in Keio, where he has many very interesting collaborators, including Mitsubishi Chemicals. He is part of a very interesting project in Keio. It is called SQAI, Sustainable Quantum AI. And it's undoubtedly one of the most interesting projects that involves quantum computing and AI in the world. And it's actually a consortium of many universities in Japan, many leading universities in Japan, University of Tokyo, Keio University, Okinawa Institute for Science and Technology, as well as one university from outside Japan, that is University of Chicago. And the interesting thing is that it has many companies, industrial companies, chemical companies, and also finance companies. And it's really a unique quantum consortium. And their Professor Sugisaki is part of the quantum optimization project. And he, in quantum computing, as many of you know, he has worked on many different quantum algorithms. And he's actually an inventor of one of the quantum algorithms that he's going to talk to us today. And so with these few words, I'll now request Professor Sugisaki to give his talk. And after that, you can ask questions and we look forward to a good discussion. Hello, somehow.
Okay, so thank you very much for kind introduction. I'm Kenji Sugisaki from Keio University, and today we have two lectures today and tomorrow. And today I'm going to talk about something about quantum algorithm for Gauss calculation on energy difference of atom molecules. But before starting my scientific talk, I would like to briefly introduce Keio University. So Keio University is established in 1858 by Yukichi Fukawa. Actually, this is the oldest private university in Japan. And we have many students, more than 33,000 of students, and more than 2,000 of tenure faculty members. And this Yukichi Fukawa is very famous guy in Japan because, as you can see, this is the 10,000 built in Japan. And this is the face of the Yukichi Fukawa. So everybody knows Yukichi Fukawa. And current president of the Keio University is Professor Kohei Ito. And he is a very famous researcher in quantum computing. And our university located around here. Here is the Tokyo. And actually, my office is in Kagawa Prefecture, which is the neighbor of Tokyo. Actually, a part of Tokyo, I can say. But anyway, as Professor Gus stated that we have a quantum computer center in Keio. And this is the overview of quantum computer center. And we have the interesting point of our group, I mean the quantum computer center, is we have 9 collaborators from companies. And we share the room and doing something together, even in the different company in the same area. We publish several papers by collaborating these different companies in one paper. So this is a very unique point. And we have actually this quantum computing center in Keio is a IBM quantum hub. So we can access some IBM quantum computer from like New York and USA and Singapore and also Kolkata or Mumbai and so on. So basically we can do something new. We try to do something new on the quantum hardware using IBM quantum machine. But today I'm going to talk about is a kind of fault tolerant quantum algorithm. So it is quite difficult to do on the real hardware. But anyway, let's start my scientific part. So my background is chemistry. So chemistry is research in chemistry is very, how to say, very diverse. So some researchers are interested in, let's say, property of biomolecule or new material or designing of drugs and so on. But basic in the chemistry research, we have 3 basic approach, I mean, synthesize and design and spectroscopic analysis. But because of the molecular synthesis, usually it takes many time and also money. So it is quite useful if we can simulate these things on the computer. Actually, the quantum chemical calculation is doing something like this. So quantum chemical calculation is the approach to solve a Schrödinger equation. is a fundamental equation of quantum mechanics to theoretically reveal the electron structure of atom and molecule. So usually we use the Born-Oppenheimer approximation in which the atom of the position of the atom is fixed, and we treat on the only the electron degree of freedom in the calculation. So in this case, the input of the quantum chemical calculation is the atomic coordinate of molecule. And then we perform some calculation to obtain to solve this kind of Schrödinger equation. Of course, solving Schrödinger equation exactly is usually impossible. So we have to introduce some approximation. But by solving some quantum chemical calculation, we obtain the total energy and wave function of the molecule at input coordinates. So if we can obtain the total energy and wave function, what we can do is, for example, we can search for stable conformations. In this case, this is this molecule incorporated in the host molecule. And we can calculate some molecular properties like excited state, excitation energy, and transition probability, and so on. And also we can calculate some reaction pathways from first principle manner. So it means that if we can accurately perform the quantum chemical calculation, it can open the door to in silico quantum chemistry, in silico chemistry research and development. But unfortunately, solving this Schrödinger equation directly is very difficult because, as you can see, actually the shape of the Schrödinger equation is very simple. We have H psi equal E psi, where H is the Hamiltonian and E is the energy, and psi is the wave function. So it means that if we apply a Hamiltonian to wave function, we obtain the energy. But the problem is because this electronic Hamiltonian includes electron-electron interaction. These are two-body interaction, so which makes the problem intractable. So this fact is very known because, as you can see, in 1929, for Dirac cases like this, the underlying physical law necessary for the mathematical theory of the large part of physics and the whole of the chemistry are completely known. But the difficulty is only the exact application of these laws, with the equation much too complicated to be solved. So we have to introduce some approximation to solve this kind of problem. Okay, so the reason why the quantum chemical calculation is existing of this interaction term. So it means that the electron moves in correlation with each other to avoid collision. And the position of electrons depends on the position of other electrons. So let's think about a simple molecule, simple model with one electron in circular motion. If we have two electrons like this, these two motions of two electrons are completely different because electron distance are different. Because the magnitude of electron interaction depends on the inverse of the electron distance. Maybe interference. Okay, so the Dirac case like this. So it's therefore become desirable that approximate practical method of applying quantum mechanics should be developed. So usually we start from the Hardy-Fox method, which is a mean field approximation. So in this case, wave function approximated by one electron configuration. So in case of solving the eigenproblem or electron system directly, if we solve the eigenproblem of an electron moving in the electron cloud formed by n minus 1 of electrons. So in this case, we obtain we calculate one electron wave function, which is the molecular orbitals. And this molecular orbital is expanded by known function, the base effect, and optimal molecular orbital to minimize the energy and solve the Hartree equation in a consistent manner. Usually, the Hartree method covers about 99% or more of the total energy. But this remaining 1% is too large to discuss chemistry. So we have to somehow recover the electron conversion effect, which is not included in the Hartree-Fock case, Hartree-Fock method. So basically, we can take into account the electron conversion effect by considering the excited configuration from the Hartree-Fock case. So in this case, the problem is determining the expansion coefficient C using a variation method. So this is the Hartree-Fock configuration for hydrogen molecule in SO3G. And we can consider some 1 or 2 excitation configuration, or in this case, we can take into account up to 4 electron excitation. And we can expand the wave function like this, and we can optimize the coefficient C by using the variation method. This is a usual chemical calculation. But the problem is, if we take into account all possible electron configurations, we can obtain the exact wave function, the numerical exact wave function within the basic being used. But the number of electron configurations increases exponentially with the system size. So let us think about the very small molecule using the conventional CCP-VDC basic set. The number of configurations can be, for instance, for benzene, which is C6H6 with 42 electrons, the number of excited configuration is already 10 to 44. So it is already impossible to even store the expansion on the memory. So this is the reason why the quantum chemical calculation, the accurate quantum chemical calculation is very difficult on the classical hardware. So we usually use some practical approaches like constant interaction method. In this case, we restrict the number of electrons to be excited. So in this case, we include only 1 and 2 excitation from the Hartree-Fock case. Or we can use the couple clock approach. In this case, we take into account the electron configuration in this exponential form. Or we can use some active space approximation like MCH method. So in this case, we enforce the occupation to be doubly occupied or unoccupied for some part, and we consider excitation within the active space. So roughly speaking, the final goal of the quantum chemical calculation is the exact solution of Schrödinger equation. But usually this is very difficult. So we start from the Hartree-Fock method, and the practical goal is a full serial method, which is a numerical-based positive wave function. And we can take into account the electron conversion effect by using CI or CC or MCHS or other approaches. And the current status of the quantum chemical calculation is gold standard approach has been established. So usually, if the wave function is well approximated by a Hartree-Fock case, we can accurately calculate the total energy by using CCST prime 6T approach. This is a gold standard approach. But such approaches become impractical if the molecule becomes very large. Because the CCST prime 6T, the communication cost scale n could be 7th power, where n is the number of molecular orbitals. And also, semi-quantitative or qualitative calculations are usually possible. But this is not always, but usually. So sometimes quantum chemical calculation fails to predict external results even qualitatively. Okay, so from this, if we can use the quantum computer for quantum chemical calculation, and if we can perform more accurate calculation or the same calculation with smaller computation cost equal to variable. Okay, so basically we in the quantum chemical calculation we solve the electron state, so the quantum state of electrons, right? And the electrons are of course the quantum mechanical particle. So basically, quantum chemical calculation is very suitable for quantum computing application because the you can see the Richard Feynman stated that we can simulate the quantum mechanics to simulate the quantum mechanics. Let the quantum computer itself be built of quantum mechanical elements which play quantum mechanical role. But this statement was in 1982 in the published version, but originally in 1981 in the international conference in MIT. But appearance of the first quantum algorithm for quantum chemistry is 2005. So we need more than 20 years to have the quantum algorithm. And this is Alan Akbuguzik. He developed a quantum algorithm for quantum chemical calculation. Actually, the full CI, and the calculation of the full CI scale exponentially on the classical computer because the number of variables increases exponentially. But it becomes polynomial if we use the quantum algorithm. But of course, this is some special case. I mean that there are several conditions to realize this kind of scaling, but still, it is very promising. Okay, so why chemistry programs so suitable for quantum computing? Because, like I said, the electrons obey quantum mechanics principle. So they can be in the superposition of many different configurations. So this kind of wave function can be realized by a quantum superposition of different configurations. So it means that, let's say, for example, in this case, we have 14 spin orbitals. So in this case, if we have 14 qubits, we can represent any electron configuration. So the memory, required memory can be reduced drastically. And there are several known quantum algorithms for quantum chemistry, but there are two major algorithms. One is a quantum phase estimation, and another one is a VQE. And basically, VQE is a quantum cluster hybrid approach. So in this case, we start from some approximate wave function psi 0 and initial gate to obtain a correlated wave function and minimize the energy. But today I'm going to talk about the QPE algorithm. So in this case, basically the computations are fully quantum except for plate fluctuation. And we can obtain full CI or cache CI eigenenergy. But the problem is the quantum stack is too deep. So there is a few difference between QPE and VQE because VQE we can obtain its expectation value or some approximate function. But if we use QPE, we can obtain the eigenvalue. So give you a few difference. So how QPE works? So let us think about we have a wave function. Assume that we have a wave function. And if we apply a time evolution operator like this, and if this wave function is an eigenfunction of Hamiltonian, in that case, the shape of wave function doesn't change. And the difference appears only the phase. So if we apply a time evolution operator to eigenfunction, equal phase difference depends on the energy. So it means that if we can determine the magnitude of phase shift caused by the time evolution, we can extract the energy eigenvalue using this equation. So this is a basic idea. So how to do? This is a typical quantum circuit for QPE, I mean the quantum phase estimation. First, we generate quantum superposition state using Agamal gauge, and this blue one are unshared qubit for the legal total energy, and red one for the wave function phrase. And first, we apply Agama gate to the unshared qubit. Okay, then we apply control unit operation. Here, U is a conventional operators. And then after that, we perform the inverse from phase transformation, from full transformation. And after that, we measure the quantity. And the measurement outcome correspond to the eigenphase of the kind of evolution operator, exponential minus IHP. So if once we obtain this phi, we can obtain the total energy. But wait, I assume that we have a wave function, right? But we don't know the wave function in the beginning of the calculation. Because if we already know the wave function, you don't have to do quantum chemical calculation at all. So we want to obtain a wave function psi, but in QPE, we need a wave function psi itself as an input. But so basically, we have to use some approximate function. So what happens if we use the approximate function in QPE? If we perform, so this phi is an approximate function which can be expanded by a linear combination of eigenfunctions like this. And if we apply a QPE with approximate function, that this is a quantity before the measurement. It transforms to the eigenphase of the Hamiltonian and the eigenfunction. And the question, we have some question which we form this one. So it means if we measure the quantity, we can obtain one of the eigenvalues. And the quantity is projected to the corresponding eigenfunction. But the probability to obtain the particular state depends on the quality of the initial wave function. So roughly speaking, if we want to calculate the ground state, we have to prepare very good approximate wave function which have very large overlap with the ground state wave function. So there are several analytical approaches for QPE. So I would like to introduce Bayesian QPE. So in this case, we have only one unshared qubit. And we can first we apply Agama gauge and perform quantum time evolution, which causes some phase shift to the wave function. After that, we apply the phase shift operator corresponding to reverse time evolution. So quantum time evolution will take a phase. After that, we apply reverse rotation. And if this epsilon equal to the eigenvalue h, in that case, we obtain in the measurement, we always obtain the zero state. Actually, we can calculate the probability to obtain zero state in the measurement of the first qubit like this. So if epsilon, this is an external parameters to be optimized equal to E, the probability of obtaining the zero state is equal to 1. So basically, we can perform this kind of Sugisaki with various epsilon values, and we can obtain this kind of plot. And the mean, this kind of plot can be fixed by using a Gaussian function. And the mean of the Gaussian function corresponds to the estimate of the true energy. And we can use Bayesian inference to optimize the area where the exact E value locates. But of course, we cannot use the eigenfunction in the as the input. So we have to use some approximate function. So what happens is something like this. The probability of obtaining the zero state in the measurement of the first qubit if we use the approximate function, the equation, we can obtain this kind of equation. So it means that this k run over the electron space. So roughly speaking, we can obtain this kind of plot and obtain some approximate estimate of E0. But sometimes if the approximate function is not so good, there are many conservations from other electron states which shift the position of the two peak from the two E value. So this means that in case of using Bayesian QPE, if we use not so good initial guess wave function, the calculated total energy have some errors. So basically, we have to use good approximate wave function in the QPE. Otherwise, in the case of textbook implementation of QPE, if the fair overlap of the approximate wave function with the full scale wave function is exponentially small, it means that exponential number of QPE should be performed to obtain a ground state energy. So it means that even if we can accelerate the QPE, exponential accelerate, we need exponential number of QPE experiments, which brings the advantage of the quantum speed up. So basically, we have to develop something new algorithm for state preparation. But this point I will talk in the tomorrow's lecture. So basically, we can, if we can generate some good approximate function with shallow quantum hierarchy from very simple quantum state, we can form the quantum chemical calculation using QPE to obtain the full scale I or Kasai total energy. But usually in quantum chemical calculation, we always calculate the total energies. But unfortunately, information on total energy are not usually accessible from experiment. The information only accessible from experiment are energy difference between two states or energies between two geometries. Okay, so it means that almost all problems focus on the energy difference or relative energy. And the total energy increases as the system size increases, but the energy difference to be discussed is not really dependent on the system size. So, for example, if we focus on the CC bond dissociation, this bond dissociation energy for CC single bond is in the same magnitude for exon or something like big molecule like protein. So roughly speaking, estimating the energy difference is much more easier because the possible value they can have is much, the region is much more small. And because quantum computer can utilize the quantum superposition state as a computing resource, if we can use some quantum superposition of ground state and etheric state, we can calculate the energy difference directly without calculating the total energies. So roughly speaking, QPE is a problem of actually determining the varying speed of the quantum axis like this. But if we are focusing on the energy difference, why don't you use the quantum superposition state of the two quantum axes to let them to run at the same time? So in this case, the difference of two speed of the running of two axes correspond to the energy difference. So this is very easy to calculate the energy difference. So in order to do this kind of thing, let us think about the mechanism of quantum phase estimation. So basically, quantum phase estimation determines the phase difference between the psi and exponential minus IET 1 psi. So it means that phase difference between before and after the time evolution. That's why in QPE we need a control time evolution operator. But in QPDE, I mean the quantum phase difference estimation, we can determine the phase difference between the two states after the time evolution to trigger the energy difference, which corresponds to E1 minus E0. In order to do, we can develop this kind of quantum circuit. So in this case, we start from the qubit inside the zero state, and this preparation gate corresponds to the preparation of the approximate wave function for the ground state. After that, we apply control excitation operators, which generates the quantum superposition ground and excited state. After that, we apply time evolution operators to make the phase shift for both the ground state and excited state, and the phase difference between these two states corresponds to the energy difference. And here I can derive some step-by-step derivations for the quantum state. First, we can generate the quantum superposition of the quantum state. And after that, we apply a control excitation operator to generate the quantum superposition ground and excited state. If we apply a time evolution operator, so this time evolution operator is control free, which causes the phase shift like this. After I apply a control reverse control excitation operator and apply a phase shift and Agama operators, the final state is something like this. So as you can see, this is just a global phase. So total information, total energy appears in the global phase, which cannot be extracted from the measurement. And what we can obtain is the energy difference like this. And the probability of obtaining the zero state is calculated like this. So it means that if the delta epsilon, which is the estimator for the energy difference, equal to the exact energy difference, the probability of obtaining the zero state becomes maximum. So roughly speaking, we can calculate the energy difference by finding the maximum delta epsilon, finding the delta epsilon value, giving the maximum probability of obtaining the zero state in the quantum circuit. So what we need for the BPDE is the second quantum Hamiltonian, of course, and also approximate function of the ground and excited state. So first, we generate some power distribution, which can be approximated by a Gaussian function. And the mean is the reference energy difference, which can be calculated using the approximate function for the ground and excited state like this. And the such area can be something like this, minus 4 to 6 times delta E reference. And we can search this area and obtain this kind of plot. And this can be fixed by a Gaussian function. This can be used as a likelihood function. And by applying the Bayesian equation for Bayesian inference, we can obtain the pocket area distribution. This can be obtained by just multiplying the two Gaussian functions. So we can easily calculate this pocket area distribution. And then after that, we can use this pocket area distribution as a prior distribution in the next step. And we can search again and again to obtain more accurate energy difference. And this is the typical quantum circuit for the single step energy gap of the hydrogen molecule. So in this case, we focus on the single step energy gap, and we focus on the MS equals 0 stage. So the single wave function can be written as alpha beta minus beta alpha, which corresponds to 1001 minus 110 in Jordan-Wigner transformation. In the spin triple state have different signs. So first, we can generate a spin triple case using this one circuit. And after that, the control excitation operator can be realized just one CZ gate acting on this that qubit. Applying this kind of circuit to generate one superposition of one static case and apply a kind of position operator, we can obtain this kind of plot. This is a simulated energy gap of the simulated value minus Fluxi value. So this is a deviation from the Fluxi value. And blue one energy different calculation using two separate BPE calculation for the total energy calculation for the ground state and static state. And red one, I use the BPDE algorithm to calculate energy difference. Because in this approach, we fit this kind of plot by finite number of measurements. So it means that there are some shock noises. So in this case, I apply the same BPD simulation with five times with the same condition. But there are some fluctuation in the measurement results, which cause this kind of some distribution. But anyway, in this case, we can calculate the energy, single triple energy gap of hydrogen molecule less than 2 kilocalories per mole error. And we can apply this approach to the ionization energies. So in this case, we use the Hartree-Fock case for the neutral state, and one excited remove the state as an initial wave function for the excited state, I mean the ionized state. And in this case, the excited ionized state is like a Koopman's approximation. So in this case, we can realize the control excitation operator by using one single case. And the result is coming like this. And of course, we can calculate the excitation energies like this. So in this case, I calculate lower singlet to singlet and singlet triple excitation for halogen substituting carbene and silane and HCHO. And of course, because the BPE or BPDE can return the Cassier value. So it means that there's no contribution from the dynamical electron configuration, basically. So basically, the BPE or BPDE using the active spec approximation, this corresponds to the Cassier wave function. So because of the absence of the dynamic correlation, the BPDE value or Cassier value have a big separate from the experimental value. But still, we can obtain using BPD algorithm very accurate excitation energy, which is very close to the Cassier value. And basically, we can apply this kind of approach if we can calculate the energy difference using conventional approach. Because in BPE, we usually assume that the preparation gate for the ground state and excited state are available. Okay? Otherwise, it is impossible to calculate the total energy. And in the BPD, we need a control excitation operator, right? But this excitation operator can be constructed by using this preparation gate like this. So it means that if excitation are energy calculation using the BPE is possible, BPD based calculation is always possible. And the benefits of using BPDE are twofold. I mean, the first one is that, of course, in conventional BPE, we have to perform two separate calculations. But in BPD, we can calculate the energy difference, just one calculation. And also, in BPE, we need a control time evolution operator. But BPD, the control free. So it means that the number of two qubit gates can be reduced dramatically by applying the BPD algorithm. and the control excitation gate can be realized so in the ionization energy, as I said before, the control excitation gate can be realized by using one single gate. And scientific energy gap, we need only one segregated excitation energy. We can use this kind of quantum circuit. So quantum circuit for control excitation is usually very shallow. But of course, we have to know the nature of the excited state. Okay, so basically BPDE is used to calculate energy difference. Okay, but interestingly, this BPDE can be applicable to calculate the total energy. How to do? We use this preparation gate acting on the flow state. So in the Jordan-Wigner or parity basis, this qubit inside the zero state corresponds to the vacuum state. Okay, so by applying the control preparation gate like this, we can generate a quantum superposition vacuum state on the target electron state. So it means that we can obtain the total energy of the n electron system as an n electron ionization energy. So basically, we can calculate the total energy by using BPE and BPDE. But BPDE, because BPDE don't require a control kind of operator. So application of BPDE for CI is much more easier compared with the conventional BPE based CI. Okay, so far, this BPDE has been applied to the energy difference of two electron states in the same geometry. So it is possible to calculate energy difference between two states because different geometry. If we can do, we can calculate, for instance, like numerical energy gradient in one calculation. So basic idea is first generate a quantum superposition on some wave function for point A and point B, and then apply time evolution operator for point A and point B separate. And if the point A and point B are very close to each other, like gradient calculation using a finite difference method, we can use the same wave function for point A and point B. And a naive implementation is something like this, just applying the control time evolution operator to control time evolution operators, like this. This is for this control time evolution operator. If the apply this time evolution, if the ancillary qubit in the zero state, and this one apply a time evolution operator for HB, if the ancillary qubit in the this one state. But unfortunately, there's no benefit because the quantum circuit for this time evolution operator is quite deep. So roughly speaking, more than 99% of the quantum circuit consists of the time evolution operator. So it means that if we apply this kind of approach, roughly the quantum depth of the quantum circuit becomes twice. We can calculate the energy difference only one calculation, but the depth becomes twice. So that it means there's no benefit. But if HA and HP share the same power strings, this quantum circuit can be constructed with small number of additional gates. So this is a conventional control time evolution operators with x0, xy, y2, y3 as a power string. We use the control time evolution, control RZ gate to realize this kind of figure. Let's think about the HA and HB share the same power string, but different question. The difference appears only the rotation angle. So basically, this kind of operation can be realized by using two RC gate and two CMOS gate instead of one CMOS control RC gate. And if we apply this kind of approach, we can calculate a numerical energy gradient with only one calculation. And there is a gradient only BSG algorithm. So if we use this gradient only BSG algorithm, we can perform geometric optimization without calculating total energy. So in this case, for instance, the energy gradient at this green point can be calculated by using this equation, and we can calculate this energy difference using BPD algorithm. And if we start from this is a numerical example for hydrogen molecules, starting from different geometries, and applying this gradient only BSG algorithm, we can obtain the Fuchsia bond length within 10 iterations. Okay, so basically BPD applicable for the energy difference, but most of the quantum chemical application for quantum computing focus on right atoms. But as you can see, there are many elements in periodic table, more than 100 of elements. So let us ask, can we compute the atomic system covering almost all the elements in the periodic table using a single quantum algorithm? So in order to calculate this kind of, especially for heavier systems, we have to apply the reactivity calculation. So we focus on the ground state property, the reactivity energy difference. So electron ground state or neutral boron atom in the non-reactivistic world is something like this. We have 5 electrons, and 2 electrons in the 1s orbital, 2 electrons in 2s orbital, and 1 electron in 2p orbital. But in the relativistic case, because of the spin-orbit interaction, these 2 orbitals, 2p orbitals, split into 2 to be half and 4 to be 3 half orbitals. So it means that the electron space occupying an additional 1 electron in 2p half and 2p 3 half have different energy. And this energy difference is known as a fine structure split. So we calculate this fine structure splitting for boron and boron-like ions. So all systems have only 5 electrons. So let's say boron and carbon cation, nitrogen dication, and so on. And we use their Coulomb and their Coulomb-Bright Hamiltonian. And we can use this kind of single-threaded determinant as a refined wave function. And in this case, we can generate the ground state wave function by using 5 NOT gates, and we can generate from superposition ground and static state by using 2 single gates. And then apply this kind of operator to obtain the phase difference between 2 states. And the result is something like this red curve we obtain from numerical estimation for BPDE. And this blue one experimental value, the spectroscopic value. If we calculate the difference between BPD value and experimental value, we can obtain this kind of plot. We use 2 different active states and 2 different Hamiltonians. As you can see, that we can obtain by using 18 qubit system with their Coulomb plus Bright interaction, we can obtain very accurate energy difference. As you can see, there are some deviation if the atom is right for right atom, but actually this is because the energy difference is very small. For instance, for boron, neutral boron, the energy difference, experimental energy difference is just 15 wave number, which corresponds to about 70 microhertz. We usually focus, say that we need a chemical precision, which corresponds to about 1 microhertz. So this value is much more smaller than the millihertz. chemical precision. But still, we can obtain very accurate energy difference using BPDA algorithm. And the difference from the experimental value is just 3 wave number. And for heavier ion, we can still obtain very accurate energy difference like this. So in this case, we use a large active phase consisting of 1s2, s2p, 3s3p, and their form by Hamiltonian. We can obtain the energy difference with about 600 centimeter inverse of RNST. Okay, in order to perform this kind of simulation, it is very important to accelerate the simulation itself. So we use NVIDIA Quantum to simulate the quantum circuit on GPU. And this is the result. As you can see, if the number of qubits for active state is just equal to 10, the acceleration using GPU is about 4 times. But if the problem becomes large, like the 18 qubit sequence, the acceleration is very significant. We can accelerate more than 40. Okay, so far I discussed a BPD algorithm, but a BPD algorithm, unfortunately, BPD algorithm has weaknesses. What weaknesses? BPDE is not projected and it requires many shocks. Okay, so as I said before, the probability of obtaining a rocket in the measurement of the answer qubit is calculated like this. So if we obtain this kind of plot and obtain the estimation of delta E, but if the approximate function is not so good, the obtained estimate of delta E is a bit shifted from the true delta E value. And also we have to perform many function execution to obtain this kind of plot. But if we use more than one ancillary qubit, we can obtain the difference of 2 eigenvalues based on the projection measure. So this is a kind of extension of the conventional QPE with n of ancillary qubits. So in this case, I use a control preparation gate, which is defined like this. So applying the preparation gate for the ground state, if the ancillary qubit in the zero state, and apply a preparation for the eclipse state by applying if the ancillary qubit in the 1 state. So first we generate a quantum superposition state and generate a superposition ground and eclipse state here, and control 3 time evolution operators and reverse time evolution. So reverse control preparation gate. If we apply this kind of quantum circuit, the phase value obtained from the measurement corresponds to the energy gap delta EJK equal EK minus EJ with the probability proportional to CJ squared and DK squared. So the probability to obtain the energy gap is equal to the conventional two separate QPE calculation, but we can calculate the eigenenergy difference using one circuit execution. And this is some result from the numerical simulation. Because this QPDE returns the eigenvalue difference, even if we use some less accurate wave function as an initial guess. So I checked this property using some 2 different initial wave functions for the singular ground state. One is using Hartree-Fock state, and another one is a 2 conventional wave function, which is much more accurate than the Hartree-Fock state. So we focus on the hydrogen molecule with the atom distance 2 angstrom and 3 angstrom. So roughly speaking, this is the intermediate region of the bond dissociation, and this region is almost bond dissociation region. So if we use the Hartree-Fock state, this is a phase and the probability. We can obtain 2 peaks, and this corresponds to the ground state, and this one is corresponds to the I mean that this is a single distributed energy gap we want to calculate, and this is the energy gap between the lowest triple state and the single excited state. And if we use more accurate wave function, we can obtain only one peak. The important thing is that even if we use for approximate wave function, the position of the peak is the same. Only difference is the probability. So quality of the reference wave function just affects only on the success probability in this case. And if we apply a single triple energy gap for H2 molecules, this will result, and this value are calculated using different Toka steps, and the result is something like this. But unfortunately, in this case, we calculate the single triple energy gap as the energy difference and single energy minus triple energy. So usually the value should be negative because the single state is more stable than the triple state. But unfortunately, if we use full approximation for the Toka condition, we can obtain some positive value. But this is because of the Toka condition. And this is the proof of the deviation from the free value. As you can see, if we use finer Toka condition, of course, we can obtain more accurate wave energies. But as you can see, the error arising from Toka condition is somewhat systematical. So this kind of systematical error can be mitigated by using algorithm error mitigation technique. So basic idea of algorithm error mitigation is something like this. In this case, I use the second order Toka condition for the academic operators, and the error scale basically scale like this. Delta t squared. So it means if we perform the QPDE with different delta t value, I mean t over m, where m the number of Toka slices, we can obtain this kind of problem. And we know that the error scale square in the delta t, we can fix this problem by using this kind of function. And we can obtain some extrapolated value of the zero Toka error limit. So this is a basic idea. If we apply this kind of algorithm error mitigation, the result is something like this. So by applying algorithm error mitigation, we can obtain very accurate energy difference. And the deviation from the free value is less than 1 kilocalorie per mole. So very accurate. And because we use this probability function, we need 3 different points, of course, to fit the function. So let me summarize my talk. So almost all chemistry problems deal with energy difference between 2 states or 2 geometries. So direct calculation on the energy difference are quite promising for chemistry applications. So, and we have proposed 4 different algorithms for the direct calculation of energy gaps. And today I have no time to discuss other two algorithms, but first we discussed some based on inference-based approach, I mean a BPDE and project PP for different information. And also I developed some annealing-based approach to calculate energy difference. The idea is very similar to the QPDE actually. And also I developed some another algorithm for the energy gap calculation for spin state energy gap using a Bloch-Schmidt wave function. So finally, I would like to thank all the collaborators and especially people from Keio University, where I'm now in, and also collaborators from Oka Metropolitan University, where I was in. and also probably from secure members, Sugisaki and Dr. Prasanna, and other collaborators. And thank you very much for your kind attention. I'm very happy to answer your question. Yeah. Yes. If we use the BPD algorithm, because the accuracy of the energy difference in BPDE depends on the accuracy of the approximation. So it means that if the approximation is not so good, the calculated energy difference can be not so good. But basically, we also develop some fungal algorithm to obtain more accurate wave function, so which is the theme of the tomorrow lecture. If we use some other fungal algorithm for the preparation of static wave function, I think we can obtain the accurate ionization energy for even for such strongly cooperative system, I think. Actually, yes. I didn't calculate N2 molecule, but we calculate like cation vesicles and HCN and so on. We have having triple bond.
May I ask a couple of questions?
Actually, demonstrating the fungal advantage is very difficult. I mean that in the BPDE, we calculate the very small molecule. And actually, if we calculate energy difference, like ionization energy for this kind of molecule, we need only 1 or 2 seconds, right? But in order to simulate this kind of thing using quantum simulator, or even if we can access the quantum hardware, it is quite difficult to obtain the accurate result. It's still difficult. But one advantage is, of course, by using this kind of approach, we can calculate the energy difference only one calculation. Otherwise, in conventional approach, we need 2 separate calculations. So this has one advantage of my algorithm. And also, basically, in the BPD or some other algorithm, we need a time evolution operator. And the scaling of the time evolution operation is n to the 4th power, basically, because Hamiltonian term scale n to the 4th power. So it means that basically, if we can obtain accurate wave function, we can calculate the energy difference in polynomial time, actually n to the 4th power. But if we obtain the same energy on classical computer, like using Sugisaki, the computational cost scale exponentially. So basically, if we can obtain the quantum advantage or not, strongly depends on whether we can obtain good approximate wave function or not. And this is an open problem. Basically, quantum chemical calculation depends belong to the QMA complete problem, which is fungal atom or NP complete. So basically, solving the one set problem on quantum computer is still difficult. Basically, it can take exponential time, even if we use a quantum computer. But this is, of course, the worst case. So maybe we can find some system in which approximate wave function can be prepared on the quantum computer in polynomial time. Also, approximate wave function cannot be prepared in polynomial time in classical computer. In that case, we can say that we can expect that we can expect the quantum advantage, I think. Yeah.
May I ask a question?
Yes.
Okay. So you said that it showed ionization energies, and they look like they're consistently higher compared to the experimental values. Do you have a comment on that? Why?
You mean the excitation energy?
Ionization energies.
Ionization energy. Yes, so basically, in this block, I plotted the difference from the Cassius value, not experimental value. That the difference is less than 0.1 electron volt. And the error mainly comes from the total decomposition error. And actually, as you can see, this HF molecule shows a larger deviation from the Cassius value. But if we use more finer total decomposition, the error becomes small. We have already examined this one. So basically, the accuracy of the ionization energy can be improved by using finer total decomposition or using more accurate initial guess-based function.
How do these calculated values compare with those when you calculate it from the Hartree-Fock calculation and use of Koopman's theorem?
Sorry, Hartree-Fock?
If you use Hartree-Fock and the Koopman's theorem, whatever ionization energies you get, how different are they from your calculated ones here?
The volume is there. Yeah. Actually, in my case, I use ionization energy at the Koopman level as an initial guess for the ionization energies. If we use, of course, the difference from the Cassius value is larger for Koopman's approximation. Applying this PPTE, we can obtain more accurate ionization energy compared with the Koopman theorem. Of course.
And your calculated values of delta E are lighter elements, and they look consistently lower compared to the experimental values. What's the reason for that? And for high Z elements, they look better. But why for low Z elements, they are consistent lower?
So this is because the total error depends on the nuclear charge. Because, roughly speaking, the total decomposition error becomes larger if the operator norm increases. So heavier ions, so heavier atoms have larger atomic charge. So it means that the operator norm of the Hamiltonian is larger for heavier atoms. So this is the reason why the light system have smaller error in the ionization energy compared with the heavier atom system.
Okay.
Yes. Yes. This one, right?
Are you asking me?
Yes.
Oh, no, not so. Where you listed the delta E values earlier for lighter and heavier elements.
Can you please repeat your question? Professor Gabe?
Yeah, I don't have any more questions.
Okay. Yes. Yes. Of course. So for larger system, of course, this hydrogen molecule, so Hartree-Fock is some kind of good approximation, especially for the equation geometry. But I focus on some demonstration. So I use the two conventional wave function, which is a very good approximation of the ground state. Of course, if we apply this approach for larger molecules, the contribution of the Hardy-Fock configuration becomes smaller and smaller. But basically, we can obtain the energy, corresponding energy gap in the probability proportional to this one. So basically, if we want to calculate the ground state using conventional QPE, the probability of obtaining the ground state is Cj squared, C0 squared. And if we use conventional QPE for the ecstatic state, the probability of obtaining the ecstatic state, the first ecstatic state, for instance, is D1 squared. Okay. So in this case, the probability is Cj squared times Dj squared. So it means the probability of obtaining the energy difference is the same between two separate QPE calculations and QPDE direct calculation using QPDE. But of course, if we use the QPE, we can confirm that the electron state is a ground state or not, because in QPE, we can obtain a total energy. So if the total energy is somewhat higher than, for instance, from the Hardy-Fock state, we can say that this state is a static state, not a ground state. So, but in the BPD, in this QPDE, such kind of approach cannot be applicable because we focus on the energy difference. So there's no upper bound. So, but still, we can obtain the eigenenergy difference using this one construct. And the construct for this QPDE is a bit deeper than the conventional QPE, but not twice, just 1.05 or something deeper than the conventional QPE. So still, I think this approach has still some advantage compared with the conventional two separate calculations using QPE. Thank you very much.